the CNC. We focus on the CNC, even though the industrial rovers on the PLC, and they are also used in the manufacturing. But PLC stands for the programmable logic controller. The industrial rovers, PLC and industrial rovers are covered in the mechatronics. Mechatronics is the senior course. But today, we only focus on the CNC, computer numerical control technology. So we have a CNC machining center in the Oliver Hall. And after we finish today's class, this lecture 1 and lecture 2, and I'm going to ask you guys to go to the Oliver Hall and to have a hands-on experience to take a look on the front. We will demonstrate on how to use the CNC for us, either this Friday or next week. Until after we finish this part, and we will talk about, as I said, we'll talk about the sheet metal forming, 2 sessions. After that, I'm going to focus on the advanced manufacturing processes, including the laser-based machining, and also this is EDM, electrical discharge machining, along with the additive manufacturing processes. Out of these 3 parts, I'm going to talk about our my research in the manufacturing processes. Right? So we will have a lot of things. So this is automation in manufacturing, and here is is the description of computer integrated manufacturing system. The computer entered this is a circle many years ago, 30 years ago, and so here's a planning under control and distributed computer system and one computer. So here is the engineering, here is the scheduling, here is the control, and so here is the planning. So this is manufacturing. Okay, so this manufacturing computer, there we have so many computers. These computers, each of these computers that controls one system. So it's for example, the parts storage and ATV control and the cell control. This is the cell control, different cell control, and assembly control, memory control, along with the finished goods, the storage. So all these things can be the controlled using the computer. So when I was young, when I was at your age, that is 30 years ago, and when I record these days, I always have tears in my eyes. Okay, so there's a long time ago. Yeah, everybody becomes older and older, right? So you guys are very young. Okay, so this being young is the most important, the most valuable the wealth you have. So learn a lot of things. So when I was young, at your age, and so at that time, the computers are not very popular. Okay, so if you have a computer, that means you are either a very, very rich guy or you are doing very, very important things. And for this is the government, and for this is for industry. When I was young. So at that time, we have for my PhD, and for this master's degree, my thesis is the distributed control system for this 3-plane drilling machine. So 3-plane drilling machine. We have 3 very, very low computers, and when compared with nowadays computers, low computers. This is microcontrollers. We have 3 microcontrollers, and we have 1 computer. So this computer controls these 3 microcontrollers. And these microcontrollers I used and this is this is what was it? This is 8098, Intel 8098. So that's a microcontroller. So we use 1 computer to control 3 microcontrollers. Each of these 3 microcontrollers controls 1 of the drilling machine. So at that time, this is 30 years ago. This is because we have so many computers here, but now things have changed. The computer technology advanced substantially. Okay, so you have more access and to the more this is advanced computers. So here is this is a system. This is a typical system. Here, so this is Okay, so this is automation of manufacturing processes. We have sensor and the soft automation, hard automation, soft automation. Mainly, this is the software, and hard automation. This is hardware. This is a transfer machine. So we have manual, computer-aided program, and you have programs if you want to do something and you want to automate it. How to automate it? And you need to write the program. And when you write the program, and you can either manually write the program or you can use a computer-aided. This is a software. At that time, AutoCAD is very, very popular. That's 30 years ago. But now things are different. We have many other very, very powerful computer design software also. But when I was young, this AutoCAD is almost monopoly all these markets. So this is a program and go to numerical control system. For numerical control, we have direct NC and we have computer NC. NC stands for numerical control. Okay? NC stands for numerical control. So here is adaptive control, and we have AC is a constraint, and AC is automation. So AC stands for adaptive control. So material handling. So this can be controlled by the system also. Manipulators nowadays, these manipulators mainly referring to the industrial robots, industrial arms. We have industrial arms downstairs. So that is for these industrial arms are for this the senior design course. Senior course is called mechatronics. So automated guided this is vehicles. So we have this material to handle materials. Robots, this is robots here. And fixed sequence, variable sequence, and played by numerical control intelligence. And so this is robots. Assembly, design for assembly, disassembly, and service. Assembly can be automated. So this assembly can be automated. Disassembly can be automated also. So in my industrial or robot class, and I have a project asking students to assembly the system automatically using the industrial robots. So that's why the flexible fusion. Flexible fusion is also can be automated and using this computer. And you can see computers are very, very important. Here is a history of automation. And the history is of automation. You can see, so here, so 1500 to 1600, the water power for metal working rolling mills for is Carnegie strips. So this is automation. And then we have handle lathes for wood, mechanical calculator. So at that time, so the boring, turning and screw cutting lathes and drill press, and we have. You can see this is mainly out. This is 1700. And that's how 1700. And people had this automation, boring, turning screw cutting lathes, drill press, and the copying lathes, parameter lathes, universal milling machines. So then 1863 automatic piano player. So this is automated, and the geared lathes, automatic screw machine, automatic bottle making machines. At that time, computers, the people did not have computers, but they can have a lot of other mechanisms to automate. This is very, very tedious, very, very time consuming on these things. And first use of word, the robot, the 1920s. And the transfer machines, mass production. After the automation, it's impossible. And so people can produce the products and in mass production. And first electrical computer machine, so the 1940s, right? The 1940s, the first computer. And this is the first digital electronic computer. So you can see the computer. After this computers, we have other people had computers, and then we have first use of word automation. So you can see the transistors. This is electronic, the component. And first prototype numerical control machine is 1952. 1952 is the time of the World War II, right? So development of symbolic language, ATT, So this NC machine becomes commercially available in 1957. After that, because electronic technologies they are growing very, very fast, and we have these integrated circuits, then industrial robots, large-scale integrated circuits, and PLC. 1968, our first PLC appears. So this is 1968. Then in 1970, the people have this is a sport welding automobile bodies with robots come into play. After that, artificial intelligence, intelligent robots, smart sensors, intended manufacturing cells here. So 1990 to 2000, we have integrated manufacturing systems, intelligent and sensor-based machines. And this is telecom, this is telecommunications and global manufacturing networks, and foundry logical devices, artificial neural network. This is internet tools, virtual environment, high-speed information system. So you can see all these automations, they are closely related to the electronics, and this is the electronics. So if we have if only after the electronics, the technology advance, and so people have these technologies to have this is the automation. So otherwise, it is impossible. Now we have industrial robots and we have artificial intelligence now. So goals of automation. Why? We know this automation is good. Why? What are the goals for automation? First one is that integrate various aspects of manufacturing operations so as to improve the product quality and uniformity. Okay, so when we do it manually, sometimes we are human beings, right? So sometimes the repeatability of our work is bad. You guys agree? You guys agree? No? Maybe you are very consistent. I am. But sometimes when I do these things, if I'm in good mood, I do these things very, very well. When in bad mood, I'm not doing things very, very well. But automation, if we automate this system, the repeatability will be much, much better. Consistency will be much, much better. Right? So this is uniformity, quality, minimize cycle times and effort involved. So effort involved. Sometimes this is very, very dangerous. For example, the spot welding. Spot welding, the glaring. So this is the very, very bright glare, right? So very, very dangerous to our to operators' eyes. So if we automate it, that is amazing. So and reduce labor costs. And then reduce labor costs. This is the first one. And second one is improve productivity by reducing manufacturing costs because the mass production and through better control of production, raw materials and parts are loaded and unloaded on the machine faster and more efficient. You can see? So it's very in the Detroit, and in Detroit, there's a lot of these cars company, right? So they build the cars and they want to automate everything. And you just initial this machine shop, they just have several people, several operators, and to make sure all the systems they are running properly. Right? So you can see they do not do anything to company. They just their role is monitoring the process of the system. Machines are used more effectively, and the production is organized more efficiently. So this is production, the automation. The third one is improve quality by improving repeatability of manufacturing processes. This is what I said. And reduce human involvement, volume, problem, and the possibility of human error. Okay? We are humans, and sometimes if we feel tired, and we cannot do things very, very consistently. So every day, because you guys are very young, I'm old. I have this experience. Because you are young, right? You are so energetic. You are energetic every day. You don't have this kind of experience. I have. Reduce workpiece damage caused by manual handling of parts. Sometimes when we do it, we can cause some damage to the workpiece. It can economize on floor space by arranging machines, material handling, and this movement and auxiliary equipment more efficiently and raise the level of safety for personnel, especially in hazardous working conditions. For example, if we want to do something for very, very dangerous, this is the manufacturing process. For example, as I said, this is sport welding. Sport welding is very, very dangerous for people. So here's the CNC operation. CNC stands for computer numerical control operations. So we have how to do it, and so here is a workpiece. This is a workpiece. So this is the tool. This is a drilling tool. And how can we automate this system? We don't want the operator, want a gentleman, or want a person to do this kind of drilling and boring things. And we want to automate it. We want to write a program. And then we feed this program onto the CNC, and we want to the CNC machine to do it by ourselves. So this is point, we can do this drilling with this drilling and boring, and point to point and straight line. They go here, go this line, million, so this million. This is the end million. This is go here, and go here. So here is the 2-axis contouring with a switchable plane. So we want to contour is a two-axis contouring. For this 3-axis contouring, the continuous path, they can do these kind of things automatically. How to do it, and you need to program. So here is the machining a sculptured surface on a 5-axis numerical control system. And so all these things can be automated. So I'm going to give you several YouTube. This is the videos, this unit, so you can have better understanding of the CNC. So a CNC machine, and CNC stands for computer numerical control. Conventionally, as we have operator, the operator decides and adjusts these various machine parameters like beat, depth card, depending on the type of job, and control the slight movement by hand. And in a CNC machine, functions and the slight is movements are controlled by motors and using computer program. Where you can select this is a different cutting parameters, and you can select the sequence of different cutting operations. You can select a lot of other things, and then just ask the computer, ask the CNC, and to do these things for you. So here we talk about the major components of NC machine tool. So here, this is the machine tool. Computers input commands, processing, and output commands. So here is the position feedback. So this is drive signal. So here is a little limit switches, and here is a work table. Right? So here is the components. So this is a computer. They need to know the position of your tool, position of your work piece. So here is an overview of numerical control. The numerical control of NC system controls many machine functions and movements which are traditionally performed by unskilled machinists. Right? So these skilled machinists not currently, and they can earn a lot of money. They can, because many plants, many companies use these people to control these machines. So numerical control developed out of the need to meet the requirements of high production rates, uniformity, and consistent part quality. So as I said, want to reduce the operator's involvement. So programmed instructions are converted into output signal, which in turn control machine operators, and such as spindle speed, tool selection, and tool movement, and cutting fluid flow. So here is NC. So by integrating, this is a computer processor, a computer numerical control of a CNC, as it is now known, the allow parts machining program to be edited. You can edit program and stored in the computer memory, as well as permitting is the diagnostics and quality control function during the actual machining. So all CNC machining begins with a part program. Maybe you need to write a part program, and which is the sequential instructions or coded commands that directs the specific machine functions. I'm going to teach you how to write a program, how to write a CNC program based on the final product, your workpiece, the original workpiece, and the final product, right? So the part program may be manually generated or more commonly generated by computer-aided part program systems. And you will use this other case. We use other CAD computer-aided design software. So this is the manufacturing. This is about CNC. So basic and CNC principles. So this is CNC. You know that the CNC will have a computer inside. So all computer-controlled machines are able to accurately and repeatedly control motion in various directions. So this is very, very important. We want to minimize involvement of people, okay, to maintain high level of this consistency and repeatability. And each of these directions of motor is called an axis. Okay, axis, multiple axes. Depending on the machine type, there are commonly 2 and 5 axes. And 5 axis machine is a very, very highly sophisticated machine. So additionally, a CNC axis may be either a linear axis in which movement is in a linear line or rotary axis with motion following a circular path. So the CNC can move in the straight line, and the CNC can also move in the arc. Questions so far? So this is straight line and arc. These are 2 basic maneuver, the operations of the CNC. So this is the most important things, and we want the functionality we want the CNC to have. So motion control. Motion control is the heart of CNC. The tool, the collision. Where is my collision? Where is my tool? What is the coordinates of my collision, of my tool? The most basic function of any CNC machine is automatic, preset, and consistent motion control. So this is the most important things. Without this one, the CNC machine is useless. Right? So this is the backbone. This is the backbone functionality of the CNC. If this one is bad, this CNC is useless. So rather than applying completely mechanical devices to cause motion as required on most conventional machine tools, and CNC machines allow motion control in a revolutionary manner. This is motor, okay? Motor, different motor. My CNC machine, the computer, look at this guy as a computer. The computer sends out the signal, and to drive this is motor to move. All forms of CNC equipment have 2 or more directions of motion. They're called axes. We said that one, right? So these axes can be precisely and automatically positioned along their lengths of travel. So this one is very, very important. Right? So if your CNC cannot position precisely, cannot move precisely, CNC is useful. So the 2 most common axis types are linear and rotary. This is what I have. I want everyone of you to put a thumb up there. Okay, I will ask you, what are the most important 2 maneuver? And 2 maneuver operations, one is linear, one is rotary. Maneuver, this linear is moving in the straight line, and rotary is a circular path. This is arc. This is for the arc. So here are the basic CNC principles coordinate system. So this is a CNC machine. So they have this is a positive X and a negative X, positive Z and negative Z. So when you use this machine, and be very, very careful, okay? So some companies, they have their own convention. And be very, very careful which one is positive, which one is negative. For x, y, z is this axis. For here, so consists of three axes positioned 90 degrees from each other. We still use is a right-hand rule. Right-hand rule x, y, z. X, y, z. We use we still follow the right-hand rule from x, y, and our sum points in the direction of v. So x, y, z. Then we use this is the right-hand rule. So here is the absolute coordinate system. So see, you can see we have origin here. Okay. So as I said in our previous slide, so precise positioning is one of the most important functionalities for CNC. So you must to be able to precise position precisely. So we need to have an origin, right? Origin here. And then we have for each point, and we will have these coordinates, a pair of coordinates. So you can just write, you know where the origin is. When you program and you write for each slide, for each command, you write, I want to move this position, I want to move that position, and then the system can precisely follow your instruction to move the tools from one position to another. So here is called absolute coordinates. Some very, very highly sophisticated systems have this is the relative coordinate system. From one position to another position, we will not use this is absolute and we use relative. Right? So here, incremental, they all called relative or called incremental. So from here to here, and we just give the incremental. Incremental coordinate system is the same as the relative coordinate system. Right? And I might ask you guys, how many coordinate systems we have? And first one, tell me absolute coordinate system. For this one, and we use the origin as a reference for all these nodes, for all these positions. So incremental coordinate system is the system that we use our previous position as a reference. Look at me, please. Incremental coordinate system is a system in which we use our previous position as a reference to denote our current position. Okay? For example, this is my original one. So this is my U1. I'm going to tell you, I'm going to so here, okay? So in X direction, I'm going to mean 5. In Y direction, I'm going to minus 45. I'm sorry. So this is just 1 second. So this is first point. 1, 3. Right? Second point is a 2. Second point is 2. From here to here in X and minus 2. Right? In X and minus 2. In Y and minus 1. So this is increment. Question? Okay. So here is my original one, and here is my incremental. So this is the original one, 1 minus 2. I come to my X will be minus 1, right? But my 3, my current one is 3. If my 3 decreased by 1, I come to 2, right? So this is my second point. So this is not my absolute coordinates, but this one is my increment coordinate based on the previous one. So dimension, imagining example. So this is dimension. So this is the positions of field holes in all piece. We have these three ones. The 3 methods of measurements are used. First one, absolute dimensioning, the reference from one point as a low level of the point. So we are positioning these three holes, which one will be used as a reference? Here, and use this as the left corner. So this is left bottom corner as a reference. You can see all these, they are dimensioned based on this one. Here, also dimensioned based on this. And the second one is incremental positions. So see, from here, right? And then next hole, this hole is positioned based on this hole. So that means from this hole, I want to go further about this length. For this one, in this direction, I want to go further about this length. So this is my second hole. Same thing, this is my third hole. So this is from the based on the previous the position. And third one is a mixed dimensioning or combination of both methods. So this is mixed, but here and they use this is a incremental dimensioning. So we have absolute dimensioning and we have incremental dimensioning, and the third one is a hybrid, is the mixed dimensioning, which is the combination of both. This is absolute dimensioning and this is incremental dimensioning. And then we talk about the basic CNC principles. So each axis consists of mechanical components such as a slide that moves. This is a servo drive motor that powers the mechanical movement, and a screw, and to transfer the power from the servo drive motor to the mechanical components. So this is a driving system. So these components, along with computer controls that guide them, are referred to as an axis drive system. This is axis drive system. It depends on how many axes you have. The basic CNC principles use a vertical milling machining center as example, and there are typically three linear axes of motion. Each is given alphabetic designation or address. The machine table motion side to side is called X, and this is Y, and this is Z, and still follow this red-handed rule, right? So here is the basic CNC principle. So this guy has three axes. So for the work positioning, so the method of accurate work positioning in relation to the cutting tool is called the rectangular coordinate system. And over the vertical mill, so the horizontal baseline is designated as X, while the vertical baseline is designated Y, and the axis is at a right angle perpendicular to both X, Y, and this is axis. So increments for all baselines are specified in linear measurements. And for most machines, the smallest increment is 1/10,000th of an inch. So this is very, very accurate. Okay? If the machine is graduated in metric, the smallest increment is usually 1/1000th of 1 millimeter. So this is very, very accurate one. So the rectangular coordinate system allows the mathematical plotting of points in space, and these points or locations are called we call the coordinates. So this is called coordinates. The coordinates in turn related in turn. This is related to the tool center and dictate the tool path and through the work. And as you can see, the coordinates. Coordinates is very, very important. Follow the tool paths. So here is the basic CNC principle. And we have this pulse train. This is the series of this pulse train. This is a very, very old one. Okay? So this old one, this is a stacking motor at that time. And then the gear, and then this is the screw and this work table. Okay? If we have a pulse, this is into the signal, the stacking motor will be rotating, and here, this gear system will be driven. And so this gear will drive, this is the lead screw. And as a result, the work table will be rotating. This is horizontally. So second one is a closed loop control for a numerical control system. So here is input. So here is this is a closed loop, and so here I will say this is open loop. I guess have you guys ever heard closed loop and open loop? For control, this is for control. Okay, the closed loop and they have the feedback. Open loop does not have feedback. Have you ever heard this open loop and closed loop? It's for control. Have you ever taken the control measurement control system? No. Okay. So the open loop here, I have an input. Sorry, I will say output. Okay, this out. I will say input for this system, and it depends on your perspective. I'll say talk about this one. This is my input. Here is my output. This out. There's no output here. But for the closed loop, so this is input, and here is my output. Here is my output. So this input and my output, and they will be compared. Right? They will be compared to see if you have achieved this is the desired position or not. But here, for this one, we do not have the feedback. So maybe I just give you one example. For example, the B-cell system. You guys know the B-cell, right? The B-cell system. You know? The missile. So the first generation of missiles, and this is open loop, right? So this is a service. So this is an airplane, and you have this is on the shoulder missile. And when you see the airplane, right? And you press you trigger your missile system, and then the missile is launched, and the missile is going to fight the airplane, right, guys? But at that time, first generation of missile is developed by the Germany, and at that time there's no feedback. If the airplane is moving, there's no feedback to control the warhead. Understand, right? But as the time goes, the people introduce this closed loop control system. Okay? So there is a sensor. This sensor is detecting the position of the airplane. If this position, actual position of airplane is different from the missile system, and the warhead will change its trajectory. So as long as there is an error becomes zero. Error becomes zero means that actual position of the airplane of target, and this is the desired position of the target, and they are become one. Okay, they become the same. Become same, that means the missile, the warhead, hit the target. So there's a closed loop. That's the first generation and the second generation. So this is a closed loop. Closed loop has this is a feedback to make sure. So this is the position. Final result is what my system wants. But for first generation missile, when I see the target, I just launch the missile. I don't care about it. Okay? Usually, if the target is moving, and the missile cannot capture it, cannot hit it. You understand that, right? Okay, good. So for the mechanical engineering students, and you will learn the closed loop control system, open loop control system in several classes, as far as I know. So you can see, okay, so this is the older one. So this is the new one. So we have, for this one, we have the feedback. We have a closed loop feedback to make sure we can control more precisely. CNC machines advantages and disadvantages. For any things, we have some advantages and also limitations. For advantages for the CNC includes this is the six aspects. First one is highly repeatability and precision. And for example, for aircraft parts, we want to use CNC. Volume of production is very, very high. Okay, it's very, very high. So they can minimize the involvement of this as the human being. The complex controls surface needs to be machined. For example, the turbines. Right? So even for turbines, even the skilled, most skilled, very skilled, the machinists, they cannot do it very well. Right? So flexibility in job change, automatic tool setting, less scrap, more safe, high productivity, better quality, and less paperwork, faster prototype production, reduction in the time. So disadvantage is setup is very high. Right? So the skilled operators, you need to have skilled operators. Computers, programming knowledge required. The maintenance is difficult. So let me tell you anecdote. When I was young at your age, so China was very poor country. Okay, at that time China wants to import. This is very high sophisticated. It's a numeric CNC system from Germany. Don't know how much money we should China should pay. You have a foundation. The German people told the Chinese people that you must use the pure gold to fill that foundation. This is the foundation. Then use that gold to change this CNC machine. That's so expensive. But that is 30 years ago. Now it seems to change a lot, right? So CNC machines are not very expensive. But I just give you the example. The types of machine for the CNC. First one is the lathes. The lathes for metal and plastics are used to produce 3D product shapes and molds. And for plastic products, milling machine for mold making and surface milling. And this is used to produce dies for die cutting printed products. So this is different CNC machines, CNC lathes and CNC milling. Milling is more important, in my opinion. It can produce more complex and more versatile features. And CNC lathes, so automated, we have CNC lathes here, okay? We have a CNC machining center, which is the most expensive one. At the same time, we have several CNC lathes and also several CNC milling machines and in the audio hall. So automated version of manual lathes is we have a computer embedded converter and programmed to change tools automatically, and this is used for turning and borrowing tool plastic, metal and plastic. Where we can do the borrowing is also rotating of the workpiece. Turning is rotating of the workpiece. So milling machine is different. Milling machine and the tool is rotating. The workpiece remains stationary. So these are different. So your CNC machine usually has 3 to 5 axes. So these are used for wood, metal, and plastic, and used to make 3D prototypes, molds, cutting dies, printing plates, and signs. And for this is milling machine. We have several of milling machines in the audio hall. CNC milling machines. And then we talk about this CNC, how CNC works. Have you guys ever heard of T and M code? No, right? Okay, T and M codes, and they are used specifically for CNC. T code and M code, and they are. And when we write the program, CNC program, we use T code and M code. So these are number values and coordinates. So the T something, M something, and they are coordinates. All this is other functionalities. Each number or code is assigned to a particular operation and typed in manually and to CAD by machine operators. And at the very beginning, and you need to type this G code and M code, and then feed these instructions and to CNC. But now the things are changing. When you do this modeling, and the system automatically change to the T code. So T and M codes are automatically generated by the computer software now currently. Okay? So then we talk about the features of CNC machines. The tool, the CNC, what are the features of CNC machine? First, the tool and the materials moves. First, the tool needs to be able to move. The material should be moved also. The tools can operate in 1 to 5 axes. Larger machines have a machine control unit which manage operations. And underscore this one, guys, MCU. MCU stands for Machine Control Unit. And maybe this is a new for you guys. Whenever we hear new things, we draw down and pay more attention to it and to internalize this one, so and we know we can memorize it. Our movement is controlled by motors. Motors is actuators, and feedback is provided by sensors and transducers. And tool magazines are used to change tools automatically. We call tool magazines also tool turret, right? And tool turret. On turret, we have multiple tools. And which tool you want to use depends on your needs. And you need to write this and in your G code or M code. I'm going to stop now. And this Wednesday, we are going to continue to talk about the CNC machine. Any questions before I end today's session? No question? Okay, everyone. I'm going to stop this.